Today we're going to find all of the associative graph products. We're going to do this by first finding all associative products where both projections onto factor graphs are weak homomorphisms. Then we're going to find all associative products where one projection is a weak homomorphism. And then we're going to find all associative products where neither projection is a weak homomorphism. At that point, we would have found all of the associative graph products. To review, a weak homomorphism from a graph G to a graph H is a mapping that sends a pair of adjacent vertices in G to a single vertex in H or to an adjacent pair of vertices in H. Next, recall that a projection from a product graph G times H to one of the factor graphs is a mapping from the vertex set of G times H to the vertex set of G that takes a vertex UV in G times H to the vertex U in graph G if it's a left projection, or to the vertex V in graph H if it's a right projection. Basically, the left projection sends vertices in the product to their left coordinate, and the right projection sends vertices in the product to their right coordinate. For three of the most commonly studied products, the Cartesian, Tensor, and strong products, the projection onto the left factor graph and the projection onto the right factor graph are both weak homomorphisms. You can think of this as meaning that we never allow two vertices in the product to be adjacent if their left or right coordinates are non-adjacent vertices, where in this video, non-adjacent means distinct and non-adjacent. For the other commonly studied product, the lexicographic product, only the projection onto the left factor graph is a weak homomorphism, meaning we never allow two vertices whose left coordinates are non-adjacent vertices to be adjacent in the product. We can see that these statements are true by examining the adjacency rules of each product. For the Cartesian product, adjacent pairs of vertices either have the same left coordinate and adjacent right coordinates, in which case they get mapped to the same vertex by the left projection and to adjacent vertices by the right projection, or they have the same right coordinate and adjacent left coordinates, in which case they get mapped to adjacent vertices by the left projection and to the same vertex by the right projection. It's never the case that a pair of adjacent vertices in the product get mapped to a pair of non-adjacent vertices in one of the factor graphs. So both projections are weak homomorphisms. For the tensor product, adjacent pairs of vertices have adjacent left coordinates and adjacent right coordinates. So they get mapped to an adjacent pair of vertices by both the left and right projections. So both projections are again weak homomorphisms for the tensor product. For the strong product, adjacent pairs of vertices are either adjacent in the Cartesian product or adjacent in the tensor product. So by our previous observations, the left and right projections must be weak homomorphisms. For the lexicographic product, adjacent pairs of vertices either have adjacent left coordinates or their left coordinates are equal. In either case, the left projection would take an adjacent pair onto an adjacent pair of vertices or to the same vertex. Therefore, the left projection is a weak homomorphism. The right projection may not be a weak homomorphism. In fact, it won't be a weak homomorphism unless the right factor graph is a complete graph or the left factor graph is empty of edges, as otherwise there's some pair of adjacent vertices in the product where the left coordinates are adjacent and the right coordinates are not adjacent, meaning the right projection maps the adjacent pair of vertices to a non-adjacent pair of vertices in the right factor graph. Now that we've reviewed weak homomorphisms, I want to show you one more thing before we get into finding all of the associative graph products. Remember that there are 8 basic adjacency rules from which graph products are determined by selecting some subset of these adjacency rules. One way to think about a graph product is as a binary vector of length 8, where each digit corresponds to one of these adjacency rules, say in the order shown here, and 1 indicates we select that rule, and 0 indicates we do not select that rule. In this way, the Cartesian, tensor, strong, and lexicographic product have the following binary vector representations. There's also another, more algebraic and more useful way to encode the adjacency rules of a graph product. You can think of the selection of adjacency rules that defines a product, for instance the selection of the two adjacency rules shown here that define the Cartesian product, as an algebraic structure with a binary operation, in this case conjunction. For example, for the Cartesian product, adjacent times adjacent equals non-adjacent, where here we denote adjacent with the symbol 1 and non-adjacent with the symbol 0, and equals with the symbol E. Note the interpretation of adjacent times adjacent is left coordinates are adjacent vertices in the left graph, and right coordinates are adjacent vertices in the right graph, where times serves the role of the logical and. And when we say adjacent times adjacent equals non-adjacent, we mean the satisfied condition that left and right coordinates are both adjacent implies the satisfaction of the condition that the product vertices are non-adjacent. Moving on, each of the 256 graph products is determined by choosing 1 or 0 for each cell in this table, not including the top left cell, which will always be fixed at equals or E. To orient yourself better around what a given multiplication table means, note that these cells in the table correspond to edges entirely within copies of the left factor graph. These cells correspond to edges entirely within copies of the right factor graph. And these cells correspond to edges that go between different copies of factor graphs. This can help you reason about what a product looks like. For example, if you have all ones in this section, your product graph will have as subgraphs copies of the complete graph on the same number of vertices as your right factor graph. Specifically, it'll have as many of these copies as there are vertices in the left factor graph. Moving on, here are the tables for the rest of the 4 most commonly studied products. With this new way of encoding the adjacency rules of a graph product, we're now ready to find all of the associative graph products. Let's start with all of the associative graph products where both projections are weak homomorphisms. The left projection is a weak homomorphism if and only if the bottom row of this table is all zeros. Otherwise, there's a 1 somewhere in this bottom row. Suppose the 1 is in the first column. This means a pair of vertices in the product graph whose left coordinates are not adjacent and whose right coordinates are the same are adjacent in the product graph, yet their projection onto the left factor graph will be a pair of non-adjacent vertices. Similar arguments work for the ones being in other positions, so the left projection would not be a weak homomorphism. Similarly, the right projection is a weak homomorphism if and only if the rightmost column of this table is all 0, and both projections are weak homomorphisms if and only if both the bottom row and the rightmost column of the table are all zeros. Since the products whose projections are both weak homomorphisms are exactly those with zeros in the rightmost column and bottom row, we only have 3 binary decisions to make to determine different products, meaning there are exactly 8 products whose projections are both weak homomorphisms. 3 of these are the Cartesian, tensor, and strong products. One of them is the trivial product that results in an empty graph. It's defined by the selection of none of the adjacency rules. 2 of the products are uninteresting products. Their tables are displayed here. They're defined by the selection of a single adjacency rule, which serves to copy one of the factor graphs for each of the vertices of the other factor graph. That is, they're just a disjoint union of copies of one of the factor graphs. This can be expressed more concisely as the Cartesian product of one of the factor graphs with the graph with no edges on the same number of vertices as the other factor graph. Here, we'll denote the graph with n vertices and no edges by d sub n. The last 2 products are not associative products, which can be verified using their multiplication tables. So the 6 associative products we have here are all of the associative products whose projections are both weak homomorphisms. We can denote the set of these 6 products by capital B. Next, let's attempt to find all of the associative graph products where exactly one projection is a weak homomorphism. Let's first suppose that the left projection is a weak homomorphism, so that the bottom row of our table must all be zeros. Suppose the top cell of the rightmost column is 1. Since this means e times 0 is 1, then if x is any of e, 1, or 0, we get that 1 times x equals 1, so the entire second row must be 1s. We can say this because we want associativity, and because we want associativity, we can also say that e times 1 must equal 1. It can be checked from the table that this product is indeed associative. Moving on, suppose the top cell of the rightmost column is not 1. Since we're assuming the right projection is not a weak homomorphism, the middle cell of the rightmost column must equal 1, or 1 times 0 must equal 1 in our table. We now have 3 other entries to choose. But again, 1 times x must equal 1 because we want associativity. So the entire second row must be 1. The only cell that we have freedom to choose is the cell e times 1. And it turns out that either choice produces an associative product. The choice of e times 1 equals 1 produces the famous lexicographic product. Altogether, we have 3 associative products whose left projection alone is a weak homomorphism. One thing to notice is that the lexicographic product is in some sense the only interesting product of these 3. The third product shown here is just a lexicographic product of the left factor graph with an edgeless graph on the same number of vertices as the right factor graph. The first product shown here is simply the lexicographic product of the left factor graph with a complete graph on the same number of vertices as the right factor graph. These only depend on the structure of the left factor graph, and that's what makes them uninteresting. Only the lexicographic product depends on the structure of both factor graphs. We can denote the set of these 3 associative products whose left projection alone is a weak homomorphism by capital L. We can repeat these arguments with the transposes of these tables. That is, when we assume the rightmost column is all zeros and find the associative products from that starting point. There will be 3 more products whose tables are shown here. These are the so-called transposes of the products we just found, where we define the transpose of a product to be the product defined by the transpose of its multiplication table. And again, only one will depend on the structure of both factor graphs. It's called the transposed lexicographic product. And again, the other 2 products can be expressed in terms of this transposed lexicographic product, making them less interesting. We can denote the set of associative products whose right projection alone is a weak homomorphism by capital R. Together with the sets B and L, we now have 12 associative products. These are all of the associative products where at least one projection is a weak homomorphism. Next, let's try to find the associative products where both projections are not weak homomorphisms. We'll denote this set by the capital letter N. We'll first need to understand what a complementary product is. Given a graph product, G complement of star H is the graph complement of the graph complement of G times the graph complement of H. Basically, the complement of a graph product is the binary graph operation defined by the graph complement of the product of the graph complements. One nice property of complementation is that the complement of an associative product is an associative product, and the complement of the complement is the same as the original product. Also, it turns out that the complement of any product where exactly one projection is a weak homomorphism is itself a product where exactly one projection is a weak homomorphism. Interestingly, the complement of a product where both projections are weak homomorphisms is a product where no projections are weak homomorphisms. To see why this is true, suppose we have a product star with both projections weak homomorphisms, and let G be a graph with at least one edge, x, x prime, and H a graph with at least one pair of non-adjacent vertices, y and y prime. Since original product star has both projections weak homomorphisms, its left projection is a weak homomorphism. Now, consider the graph complement of G times the graph complement of H. Since star's left projection is a weak homomorphism, x, y, x prime, y prime is not an edge of this product, as x, x prime is not an edge of the left factor, the complement of graph G. Since it's not an edge of this product, it will be an edge of the complement of this product, which is nothing more than the complementary product of G with H. Yet y, y prime is not an edge in H. Therefore, the complementary product's right projection is not a weak homomorphism. In a similar manner, we can show the complementary product's left projection is not a weak homomorphism. As a result, the 6 products formed by taking the complements of the 6 products in the set B are distinct from all of the associative products we've seen so far, because they each have neither projection being a weak homomorphism. And they're also distinct from each other because the complement of a product is the product itself, and the 6 elements of B are distinct. We now have 18 associative graph products, and our set N of associative products where both projections are not weak homomorphisms has 6 elements so far. But we're missing some elements of N, specifically those products where both projections are not weak homomorphisms and whose complementary products also have the property that both projections are not weak homomorphisms. It turns out that the only 2 associative products that fit this description are the modular product and its complement, whose multiplication tables are shown here. As an exercise, I encourage you to show that the only 2 associative products with this property are the modular product and its complement, and to determine what is the effect on the multiplication table of taking the complement of a product. We have now found all of the associative graph products. That's all for this video. Thanks for watching.